Okay?
Yeah.
All right. Hit me with what number? We're in 3, 5, right?
Yeah. Number 15.
Okay.
E to the x over y.
3.
No, e.
Okay. E to the x over y.
No. X over y in the power.
Okay.
And then equals x minus y.
Equals x minus y. Okay. And we just want the first derivative out of this? Okay. So we'll start by taking the derivative with respect to x for both sides. So far, so good. In the first, or the left side, the left-hand side, to differentiate e to the x over y, we need to use chain rule. Very good. So the derivative, the outside function is e. So the derivative of e is just, and then times the derivative of the inside. So far, so good. And on the right-hand side, the derivative of x is 1. Derivative of y is 1 dy dx. Very good. I'm not going to bother writing the 1. Is everybody cool with? Okay. Now, to differentiate x over y, what do we need to do? We need to use the quotient rule. So it's the bottom times the derivative of the top minus the top times the derivative of the bottom, all over bottom squared. So far, so good. The derivative of x is just 1. So I'm not going to bother, just write y rather than y times 1. Everybody cool? And the derivative of y is dy dx. So I'm going to just have x dy dx. So we have that. So far, so good. At this point, the calculus is done. Although for this problem, I need to get the dy dx by itself still, so there's some algebra cleanup that I have to do for this. Lucas, you good so far?
Yeah.
Okay. So I guess what I would do first is, I hate this fraction thing going on. I'm going to take care of that straight away. I'm just going to multiply both sides by y squared. And I'm going to distribute the e to the x over y through to both sides. And then I'm going to add the y squared dy dx to this side and subtract the y e to the x over y over to the other side, so I can get the dy dx onto the same side. Are you okay with what I did there? Now that the dy dx's are on the same side, I can factor the dy dx off, and then divide both sides by the y squared minus x e to the x over y. And that should be my final answer there. Can I do any reducing on that? Probably would say no since I circled it. Is it okay to do this? No, very good. Why not? Perfect, yes. Because there's addition and subtraction going on inside the numerator denominator. I can't reduce like that. I think I caught somebody doing that at one point in something recently. Figured I'd remind everybody about that again. Lucas, does that feel okay? Again, like the calculus piece was not trivial, right? There was a lot to do there. And then the algebra cleanup was kind of a lot. But we got there. You know. Hey. 13? You're going to have to read me the problem, but yes.
Yeah. 4 cosine x times sine y.
This, okay.
Equals 1.
Okay. And we're just looking to find the first derivative. Okay. So again, start by differentiating both sides. Now, probably what I'm going to do here is I'm going to think about the 4 at this spot. So just going to kind of come along for the ride for everything. But you can think about it inside. It doesn't really matter a whole lot. So to differentiate cosine x sine y, I need a product rule. So I'm going to have 4 cosine x times the derivative of sine y, which is cosine y dy dx. And then I'll have 4 sine y times the derivative of cosine x, which is negative sine x. And the derivative of 1 is just 0. So I'm going to add over the 4 sine y sine x. I'm adding because it's really a negative there. And then we'll divide over afterwards the 4 cos x cos y. So I notice that pew pew, those guys can go. And I recognize sine over cosine is tangent, and sine over cosine is tangent. So I could probably simplify this as tan y tan x. Would be like my best answer, probably what the back of the textbook has and what a multiple choice solution would look like. You okay on that, Peyton? Yeah. Adrian, what's up? You look like you really want to ask something. Come on in.
I was like, didn't you subtract it to get to like the other side?
So
Minus 4 side.
yeah, so I added, right, because this whole thing is negative. So I added that over the 4 sine y sine x, and then I divided.
Yeah, I saw you divided. I just thought like, since there's a plus sign in the middle, you'd subtract it.
Yeah, yeah. So this negative really means that like, yeah, I can do that kind of thing, right?
Nice.
Hi.
So it's like dy over dx multiplied by the entire thing or just by the cosine?
Just by, like, this stuff is all multiplied together. Right, that's just like a bunch of stuff multiplied together. Is that what you're asking? Alright, we feel okay? Questions answered? A little better? Guys, once you drop your stuff off, your cell phones, and grab your card, and we'll pass these guys out. I mean, drop your stuff off. So. And I would say, guys, for this one, you probably do want a calculator. I mean, it's doable without one for sure, but. That's okay.
But I think it might be like, I don't know, I think it was.
Story of your lives, right?
It's too hard.
So in this section 3.6, we've been talking about how to take the derivatives of logarithms. So initially we saw our 2 rules for differentiating logarithms. The derivative of log base a of x is 1 over x times the natural log of a. And the derivative of the natural log is just 1 over x. And we saw that, like most of these most of these logarithmic derivatives are going to be chain rule type problems. But we saw in certain circumstances, like in example 5 here, I could take a particularly nasty looking derivative that has like 2 chains and a quotient in it, and use my properties of logarithms to like make that process considerably simpler. I can eliminate having to do a quotient rule. All my chain rules are now logarithm chains, which are pretty easy chain rules to do. And the question is, can I take that and apply it to something like this? So this would have been like something similar to the problems you saw on the last page of that derivatives worksheet, right? So if you look at this, I see a product rule, a quotient rule, two chains. I see a lot of grief in my future, right? Looks pretty nasty. What you can do, not required, but what we can do, what if there's a natural log in front of that whole big thing? What if we had that to start with? That would allow us to use our properties of logarithms to like unpeel that nasty, nasty derivative and make life a little bit simpler. It leaves us a little bit more algebra cleanup at the end, but the calculus is massively simplified. That's what we're going to show you guys how to do. So this process is called logarithmic differentiation. So what we'll do is we'll start by taking the natural log of both sides of this equation. Is everybody okay with what I've done? And again, if I'm doing it to both sides of the equation, no problem. Now, once I've done that, I'm going to apply my properties of logarithms on the right-hand side. So when I'm doing my properties of logarithms to expand a logarithm, the order in which I apply my properties typically is going to be quotient, product, power, kind of in that order. So if I look here, I see a quotient property. So that's going to turn into the natural log of the numerator minus the natural log of the denominator. Everybody feel good there? In this logarithm, I see I have a product property. So I can rewrite that as natural log x to the 3/4 plus natural log of square root x plus 1. And then I still have this last guy, no product property going on there that I want to tackle. I mean, yes, technically to the 6th. You got 6 of those 6 multiplied together, but like, no thank you. Go ahead, you can go. I'm just going to handle the power property on the next step. Are we all okay to how I've gotten to here? Have I done any calculus yet? No. I haven't even started the derivative piece yet. I've just done algebra. Now, I'm guessing that after doing 1 or 2 of these properties of logarithms and this expanding a logarithm technique is going to come back to, because I know you practice it in Algebra 2 and pre-calculus. If you can do it all in one step, go ahead and do that. You don't have to do like one property at a time like I've done here. These are notes, so I'm going to do it that way. But if you're like, you look at that thing and it's like, yeah, I can see what the expanded form is going to look like without having to go like through a bunch of intermediate steps, go ahead and jump right there. That's fine. Do you guys get what I'm saying? How many of you looked at that and were like, okay, I can see what the final answer is going to look like? Not yet? That's okay. All right. So now we're going to start the calculus piece. to do that. Everybody okay? Just taking the derivative of both sides. I'm just showing some work. Start with the left-hand side. What's the derivative of the natural log of y with respect to x? It's going to be 1 over y times dy dx. Okay, now let's tack this piece. The derivative of the natural log of x is 1 over x. The derivative of the natural log of x squared plus 1 is, well, times the derivative of x squared plus 1. I would think about it using this rule, derivative of the inside divided by the inside. That's pretty nice for these logarithmic differentiation problems. So the derivative of the inside is just 2x over the inside. Like how nice and neat that is. That's a really easy chain rule to do because of the form of the natural log. Like I love that. Trading out the quotient rules and everything I had before for these kind of chain rules is like good trade. So the derivative of the natural log of 3x plus 2. 3 over 3x plus 2. Everybody feel good there? So now, we can multiply both sides by y to get the dy dx by itself. And I'm going to do some cleanup here. So far, so good? But I don't want a y here, right? What do I really want here? That. Because that's what y is. At this point, for your response question, you can stop. That would be finished. If it's multiple choice, probably the answer isn't going to look like this. You'll have to like grind through some simplification. But if it's a free response, once you've gotten that y out of there, you can stop. Anthony, you had, was that going to be your question?
I was going to ask you to stop.
Yeah, I beat you to it. But yes, that would be a fine stopping point. You know, if you make a common denominator and you multiply things through, there's obviously going to be some simplification that can happen. Do you need to do that? Not unless it's a multiple choice question where you're trying to get to figure out which one A, B, C, or D is the answer, right? And this type of question would be a poor candidate, in my opinion, to make a multiple choice question. Too many places to like make a mistake and end up not getting anything in the answer. Is everybody okay with that idea? So, again, the process to do logarithmic differentiation, take the natural log of both sides, use the laws of logarithms to expand your logarithms out, implicitly differentiate with respect to x, and then solve the resulting equation for y prime. So, is that multiply both sides by y is usually what that means. And then make the substitution back in so everything is in terms of this. So let's do this. Right? Oops, that's not the one I wanted. I wanted this one. So if we look at some of these, some of these look terrible, right? Now, logarithmic differentiation is a good candidate to handle some of these. Not all of them, but some of them. In particular, you know, like this is not a great, I mean, it's okay, but not a great candidate. And the reason is you have the chains around the quotients. Not as great. This guy, great candidate for logarithmic differentiation. That'll handle it really nicely. This guy, pretty good candidate. Will handle that pretty nicely. Not the best, but pretty good. You'll still have, like, this guy's still going to be a bugger to deal with. And this guy's still be a bugger to deal with, but, like, not bad. It's okay? So I think I had one more example here on this page. So it says differentiate y equals x to the square root x. Do we have a derivative rule to handle x to the square root x? We have the x in the base, which looks like a polynomial, right? Like x squared, x to the third, whatever. But we have an x in the exponent that makes it look exponential, like 2 to the x, 3 to the x, e to the x. This has x's in both spots. It's neither one of those. We don't have a specific rule to handle this. What do we do? Logarithmic differentiation will allow us to separate the exponent from the base, right? And that's the trick on this. So you can't like double chain rule it. That's not gonna, I see what you're saying, but it won't work because we don't have a rule for x to the x kind of thing. But if we do this, allows us to rewrite it using the power property of logarithms. And now, if I take the derivative of both sides, no longer do I have a derivative that I can't handle using the rules that we currently have. So the derivative with respect to x of the natural log of y, 1 over y dy dx. To do the derivative of square root x times natural log of x, I need to use a product rule. So we have square root x times the derivative of the natural log of x, which is 1 over x, plus the natural log of x times the derivative of the square root of x. Everybody okay here? Now I'm going to clean this up a little bit before I proceed because I notice some reducing can happen here. what's square root x times 1 over x going to be? How's that going to reduce down? X to the negative 1/2, or you could think about like 1 over the square root of x. Either way, thinking about that is fine. So what I have is, I'm going to rewrite this with a common denominator with this guy. So it's going to be 2 plus natural log x over 2 square root x. You guys see where the 2 came from? Making a common denominator, this is 1 over 2 square root x. This is 1 over 1 squared x, so I make a common denominator. So then all I have to do is multiply the y back to both sides. That ought to do it. Right, I just multiply both sides by y.
You mean y from the beginning?
Mm-hmm.
Wouldn't it be ln x or
Y from the beginning. So no ln on it. Does that feel okay, Peyton?
Wait, so will you ask us find the natural whatever motivation, or do we just need to know like we should do this?
So I would say that you can use logarithmic differentiation when it suits you. If I want you to do it, like I've written a problem intentionally that like, this is a problem you should use this on, I will probably say in the directions to use logarithmic differentiation to find the derivative. But you're welcome to use it in any context that looks like a good context to you. So it's not limited by instruction. If you're like, ooh, this looks like a good candidate, I would do logarithmic differentiation on this. That looks easier than plowing through it the other way. You're welcome to do that, even if you're not instructed to do so.
How do you know if it's a good?
So what I would say is, good candidates for logarithmic differentiation are ones where the chain rule is like the last thing you'd be doing. So if I go back and I look at this problem, the first thing I'd have to do is the quotient, right? And then the product, and the chains are going to be the last pieces I have to handle, right? That makes it a good candidate, as opposed to something like this is a terrible candidate, because the first thing is a chain, and then a chain inside, like you can't get rid of chain rules with logarithmic differentiation. What you get rid of is product and quotient rules. Or if your product and quotient is like stuck inside of a chain, right? Like this quotient, well, this quotient and this quotient are stuck inside of chains. Logarithmic differentiation is going to help you get rid of those quotient rules. Does that, you kind of see what I'm saying in terms of like good candidate, bad candidate? And some of it's just going to be by building some intuition by doing problems, right? Like at first, to be like, I don't know if it would be good or not, it's hard to tell. And that's fine. That's why it's like, when I want you to do it, I'm going to tell you like, do it for this problem. And everywhere else, it's going to be like, when you feel like if you'd like to do it, you're welcome to do it. And if you don't want to, you don't need to. any problem that can be done with logarithmic differentiation, short of a weird case like that x to the square root x problem, can be done without logarithmic differentiation. It's just a matter of like, is one way maybe a little bit cleaner than another way, but they're both effective. Does that help?
Yeah.
Okay. So again, like the logarithmic differentiation is a option. It's not an option you probably even use widely. It's an option you probably use lightly. But when you see it, like, ooh, that really makes life a whole lot easier. It's, you know, when it's a good candidate, it's a really good candidate, and it's a real time saver. And when it's not, it's like, oh, this isn't getting me anywhere, I can abandon it pretty quickly. So it's one of those things like I would spend 5 seconds at the start of the problem just going, is this a good candidate? And looking at it and be like, how many rules are in here that I can get rid of by doing, you know, logarithmic differentiation? If it's like, I get rid of the quotient 2 products, sounds like a good deal to me. If it's like, it doesn't really get rid of any, gets rid of 1 product rule, maybe not bother with it. Does that make sense? Okay. So the other piece that we have that I want to talk about today is section 3.7, which are just like story problem application problems. So there's no new concept, nothing new. All we're going to be doing is using our derivative rules and some like basic kind of problem solving skills. So I just am going to do kind of walk through one example, and I'm going to show you some stuff on the calculator that you can do that makes some of this stuff really, really easy to handle. So if you have a calculator with you and you want to follow along on that, I invite you to do so. If not, you can always come back and like, you know, at home, pull up the YouTube and watch this part with the calculator handy and follow along. All right, we have that the position of the particle is given by the equation s equals yada yada yada. Find the velocity at time t. What's the relationship between position and velocity? Velocity is the first derivative of position. That's the order you're looking for. So we just need to take the derivative of this. What's the derivative of s? That's it for A. Woo! That was rough. Find the velocity after 2 seconds. What's that? -3, and we're in meters per second, I think. And then after 4 seconds, (16 times 3 is 54, minus 48 is 6, plus 9 I think is 15. Everybody okay with what I did? When is the particle at rest? What does it mean for something to be at rest? It's not moving, which means velocity is 0. So to solve that, what are we going to have to do? Okay, would you do anything first? What's that? Or divide both sides by 3, right? We don't, I mean, you could factor it out, but we're doing it to both sides. If we're solving here, we can just do that, right? Now the factoring becomes a heck of a lot easier because you shed that leading coefficient. Everybody happy with that? D says, when is the particle moving forward? That is, it has moving in the positive direction. What does that mean? What's greater than 0? Velocity, very good. How do I solve an inequality like that? I mean, v of t is quadratic. Remember how to solve a quadratic inequality? Yeah, you're going to build like a sign diagram. So I just need to pick some values of t. Now I don't have to worry about anything less than 0, right? Because we're talking about time. So I'm just going to pick a test value, say at like 1/2, 2, and 4. Now, why'd I pick 2 and 4? I already did the computation for v of 2 and v of 4. I'm just saving myself some time. So I know that v of 2 is negative and v of 4 is positive. I just now have to check v of 1/2. So when I plug 1/2 in, I'm going to get a -6 here, plus 9, that's positive, plus another positive, I know that's positive. I don't really care what the number is. I can just see that it's positive. Is everybody good there? So, when is the particle moving forward? From 0 to 1, or from 3 to positive infinity. Still okay? Very algebra 2e pre-calc feeling, right? We had to do one little piece of calculus to find the derivative, but from here on out, it's like doing stuff that we hopefully feel pretty good about. Draw a diagram to represent the motion of the particle. I don't want to be honest with you. I wouldn't ask you to do that. I mean, it's like, you know, like we're at time t equals 0. We're moving forward to like 1/2. And then like we turn back, you know, and then we're going to like t equals 2, and then we turn again at like t equals 3. Something like that. Because the particle is just moving back and forth on the x-axis. Find the total distance traveled by the particle. In the first, what does it say? 5 seconds. What's the catch here? What happens? What does the particle do in the first 5 seconds, though? it stops and then turns around. If I want total distance, I have to count the distance forward and the distance backwards, right? So, yeah, we're talking about displacement. Good job, physics talk. So really we want like the absolute value of S, right? So the way I would do this is I would look at the distance from 0 to a half, and then I'd add to that the distance from a half to 3, and then I'd add to that the distance from 3 to 5. Everybody's okay with that? So if I just take the absolute value of the displacement, the change in position over those 3 time intervals and add them up, that'll be the total distance traveled. Notice I don't have to worry about, like, am I subtracting the bigger one from the smaller one? I don't care because I'm just taking the absolute value of the thing afterwards anyway. Everybody's okay? I think that'll do. And then G, find the acceleration at time t after 4 seconds. So how do I find acceleration? Second derivative or the first derivative of position. So what's the equation for acceleration?
6t minus 12.
Perfect. So then A of 4 is just going to be 12 meters per second squared. I don't want to graph these. We'll do that in a second because I'm just going to use the calculator to do it for us. It says, when is the particle speeding up and when is it slowing down? How do I find that? Yeah, so we're looking at hold on. That's not right. Why is that not right? Physics people, why is that not right? Yeah, that would be for velocity. This says speed. What's the difference between speed and velocity? So if it's going this, like, velocity is negative, but acceleration is also negative, that's speeding up, right? If velocity is positive and acceleration is positive, that's also speeding up. If they mismatch, that's going to be slowing down. So we need A of t equal to 0. We'll do it in a sec. Shh. So if I do that, I'm going to have negative and positive. And then we said V of t was negative from 1 to 3. and v of t was positive from 0 to, 0 to 1, and then 3 to positive infinity. So where do they match? Let's do this. So from that's for velocity. That's for acceleration. So where are we speeding up? Just from 1 to 3. Right, because I think it asked only for over 5, right? Oh, no, it didn't. It's period. You're blessed.
I gotta go get my friend's stuff. He's unconscious.
Sure. Shoot. Oh, we have a couple of seconds. So, calculator. Let's show you what this bad mama jamma can do. Or not, it wants to be. So for this problem, I can do the majority of that problem on my calculator. You know what? Let's just do this next time. Remind me at the start of class next time to go through the calculator piece. Let's just do it next time. I feel like I'm gonna be rushed. I don't want you guys to rush. I want to do this like nicely and in earnest. So for next time, homework quiz from 3-6. So it should know how to take the derivative of logs. I will have a logarithmic differentiation problem where I ask you to do it via logarithmic differentiation. The directions will say that. Although you're welcome to do logarithmic differentiation in other places if it suits you. Everybody cool? Okay. And I think this will be the last, next time will be the last homework quiz before the next test. So we still have 3-7, I won't do a homework quiz on that. We have 3-10, I won't do a homework quiz on that.
So, the test will be like next week, probably?
Depends on timing, the earliest would be end of next week.
Right now, but I have. Yeah.